This videotape deals with graphing in 2 dimensions, especially graphing linear equations. Most of you are familiar with the idea of a rectangular coordinate system, also called the Cartesian coordinate system after the mathematician Descartes. The idea is that we take 2 mutually perpendicular number lines. We can run one of the number lines horizontal, like that, and another one vertical, so they meet at right angles. The point where they intersect we call the origin. The horizontal number line we generally call the x-axis, and the vertical number line we call the y-axis. These 2 number lines cut the xy plane, the blackboards here, into 4 quadrants. Starting in the upper right, we call this quadrant 1, and then numbering counterclockwise, quadrant 2, quadrant 3, and quadrant 4. They intersect right angles at the origin. Okay, we take the horizontal axis to have its positive direction to the right. Okay, this is arbitrary, but this is the way we usually do it. And the vertical number line has its positive direction up. Okay, now with this system, it is possible to locate any point in the plane by means of an ordered pair of real numbers. Okay, the numbers can look something like this. Say x comma y, an x coordinate followed by a y coordinate. These numbers sort of give the location of a point or its address. If you could imagine, say you have a man standing at the origin here, and we want to send him to some point in the plane. And he looks at a sheet of paper on which he has written the numbers x comma y. This tells him where to go. If the x coordinate is positive, he moves to the right. If the x coordinate is negative, he moves to the left a certain number of units, whatever it happens to be. If the y coordinate is positive, he moves upward. After he takes care of the x, the y coordinate is positive, he then moves upwards. The y coordinate is negative, he moves down. Okay, so if x is positive, he moves up. If x is negative, if x is positive, he moves to the right. If x is negative, he moves to the left. If y is positive, he then moves up. If y is negative, he moves down. Of course, he could follow the y directions first, and then after he's finished with that, then follow the x directions. Now, this may seem like a very simple idea, and most of you have seen this idea before, but it's a very important idea in mathematics. What we're doing, essentially, is establishing a one-to-one correspondence between the points in the plane, which is essentially a geometric idea, and ordered pairs of numbers, which are basically an algebraic idea. So we're setting up a link between the points of geometry and the numbers of algebra. And it's a one-to-one correspondence in that each point in the plane is associated with one and only one ordered pair of real numbers, and each ordered pair of real numbers corresponds to one and only one point in the plane. Let's say somebody is given the set of coordinates 3, 5. Okay, let's plot that point or graph the point 3, 5. Okay, let's say 3, 5. Let's move over here. We have a blank system here. We have the x and the y axes. They intersect at the origin. Okay, so he sees 3, 5. Since x is positive, he moves to the right 3 units. He's starting at the origin. He moves to the right 1, 2, 3 units. Then y is positive 5, so he moves up 1, 2, 3, 4, 5 units. And here we have the point 3, 5. We have graphed the point or plotted the point 3, 5. Of course, he could have first moved up 5 units and then to the right 3 units. It doesn't matter which direction he takes first. The important thing, when x is positive, you move to the right. When x is negative, you move to the left. When y is positive, you move up. When y is negative, you move down. Okay, what about the point -3, 5? Let's plot that point. X is negative, so he starts at the origin, he moves to the left, 1, 2, 3 units. Then y is positive, so he moves up, 1, 2, 3, 4, 5 units. bringing him over here to the point -3, 5. This, by the way, of course, is the first quadrant, the second, the third, and the fourth. Okay, let's look now at the point -3, -5. Starting at the origin, he moves to the left 3 units and then down, because y is negative, down 5 units. 1, 2, 3, to the left, 1, 2, 3, 4, 5. To get to this point, -3, -5. And let's also look at the point 3, -5. He will move to the right 3 units and then down 5 units. To the right 3 units and then down 5 units over here. Okay, what if the point were 4, 0? Okay, this means he moves to the right 4 units. He's starting at the origin. He moves to the right 1, 2, 3, 4. Y is 0, so he does not move up. He does not move down. He stays right here on the x-axis. Here we have plotted the point 4, 0. In a similar manner, let's say it was 0, 2 that we were interested in. If x is negative, you move to the left. If it's positive, you move to the right. It's 0, so he stays right here. Doesn't move to the left, doesn't move to the right. Then y is positive. He moves up 2 units to get to the point 0, 2. And of course, we could also handle fractions in the same way. Now, it's important to realize that in the first quadrant, the points will always have a positive x-coordinate and a positive y-coordinate, because how do you get into the first quadrant? You'd have to move to the right and then up. Okay, in the second quadrant, points will always have a negative x-coordinate and a positive y-coordinate. Negative x-coordinate and a positive y-coordinate, because you're moving to the left and then up. In the third quadrant, the x-coordinate and the y-coordinate will both be negative, because from the origin you'd have to move to the left and down to get into the third quadrant. And finally, in the fourth quadrant, it's a positive x and a negative y-coordinate. You're moving to the right and then down. Okay, so in this manner, by using this rectangular coordinate system, we can associate with every ordered pair of numbers one and only one point in the plane. Every point in the plane has one and only one ordered pair of real numbers associated with it. This business of ordered pair, if you're wondering why am I saying ordered pair of real numbers rather than just pair of numbers? Okay, ordered pair because 3, 5 does not represent the same point as 5, 3. 3, 5 means move to the right 3 units and then up 5 units, whereas 5, 3 would mean move to the right 5 units and up 3 units. Okay, 3, 5 and 5, 3 represent different points in the plane. That's what I mean by an ordered pair of numbers. The order in which the numbers appear is important. The first number always represents the x-coordinate, telling you how much to move to the right or left. The second number represents the y-coordinate, how much to move up or down. Okay, in a similar way, we could also be given points in the plane and be asked to write down the coordinates of these points. Okay, and that's what I have done. Here, I have labeled 4 points in the plane, and I would like you to try to write down the coordinates of these points, the ordered pair of real numbers that goes with each of these. I'll give you a moment to look at this. If you would like some more time to work on this, you can, of course, shut the videotape machine off and turn it back on when you're finished. The first point, A. We are trying to write down the coordinates of this point. We noticed that if the man was starting at the origin, he would move to the right 2 and up 3 to get to point A. Therefore, the coordinates are 2, 3. Not 3, 2, which would be over here, but 2 over and then 3 up. Now let's look at point B. Starting at the origin, he moves to the left 2 units, so that's -2 for the x-coordinate. Then he moves down 1 unit, -1 for the y-coordinate, -2, comma, -1 for point B. Okay, for point C, he moves 1, 2, 3 units to the right, and down appears to be 1.5, -1.5. 3 over, 1.5 down to get to point C. And finally, point D, he starts at the origin. He does not move to the left. He does not move to the right. 0 for the x-coordinate. He then moves down 2 units. -2 for the y-coordinate. 0, -2. Okay, now that we know how to graph points or plot points, we would like to move on and be able to graph linear equations or graph first-degree equations in 2 variables. Okay, by that I mean something like this. A first-degree equation in 2 variables is an equation that looks like this. ax plus by equals c. A, B, and C are constants. A and B are not both 0. This is a first-degree equation in 2 variables. So, for example, something like this. 3x plus 2y equals 6. A is 3, B is 2, C is 6. You could also have something like this. Y equals 3x minus 2. Since it is possible to rewrite this in the form 3x, or minus 3x, plus 1y equals minus 2. Where A is -3, B is 1, and C is -2. You could have also done it the other way. 3x minus 1y is equal to plus 2. But we see it comes under this general form. And something like this, y equals 4, could be thought of as 0x plus 1y equals 4. We cannot have both A and B equal to 0. Okay, but either A or B can be equal to 0. Now we are interested in graphing this type of an equation. Okay, now a graph of such an equation is essentially a picture of its solution set. So we'd have to have some idea of what solutions to an equation like this look like. Okay, now if you had a first-degree equation in only 1 variable, this you're a little more familiar with, we know about solutions to equations like that. A first-degree equation in 1 variable, something like 3x plus 2 equals 8, 3x equals 6, x equals 2. The solution would be just one number. Okay, now by a solution to something like, 3x minus 2y equals 5. A typical solution here would be a pair of numbers, one for the x and one for the y, which satisfy the equation. For example, we could have, let's just try to get one. Let's let x equal 1 and see what happens when we let x equal 1 here. If x equals 1, we get 3 times 1 minus 2 times y equals 5. 3 minus 2y equals 5. Minus 2y equals 2. Y equals minus 1. So a typical solution would be x equals 1, y equals minus 1. We could write this as the point 1 minus 1. The first number, of course, represents the x value, and the second, the y value, in such a way, okay, by plotting this point, we would be plotting this particular solution to this equation. Okay, now there are, in fact, many solutions to this equation. 1 comma minus 1 is only one of them. If we were to let x equal 3, we would solve, and we would see that 3 comma 2 is also a solution to this equation. If x equals 3 and y equals 2, we get 9 minus 4 is equal to 5. And there are many others. Let's see, 7, 8 happens to also work. 3 times 7, that's 21 minus 16 gives us 5. In fact, by choosing any x value, the ones that I've given you sort of come out nicely. You pick these x values, the y values come out to be whole numbers. But you could pick any x value you want. You could pick x equal 2. Okay, your y value wouldn't come out as nicely, but you would get a y value. Each of these points represents a solution to this equation, and the graph of this equation will be a picture, sort of all these solutions. Okay, a picture of the solution set. Now let's try to plot these points here. My axes look a little strange. Let's see what I can do to fix it. Okay, we have, let's mark off. The point 3, 2 was one of the solutions to 3x minus 2y equals 5. 1, 2, 3 over, 2 up. 7, 8 was another solution. And 1 minus 1 was also a solution. I could keep getting other solutions, let x be different values, and get what the y values are. It would turn out that all of the points that I would get, in this case, would lie along a straight line going through these points. Okay, it's going to be a little hard to draw without a ruler. Something like that. This is not a coincidence. Okay, the points that I have written down, these were all solutions to this equation. Every other solution would also lie on a straight line through these points. Now we know that 2 points determine a straight line. Okay, so actually anything beyond these 2 points was sort of extra information. Such an equation, one that's in this form, ax plus by equals c, is called, aside from being called a first-degree equation in 2 variables, it is also called a linear equation, since the graph of such an equation, the picture of all of its solutions, okay, is always a straight line. Okay, a first-degree equation in 2 variables is also called a linear equation. Its graph is always a straight line. Okay, knowing that, then once you're beyond 2 points, you're really doing it just as a check. You just need 2 points. Anything else will just check to make sure that your first 2 points say were correct. By the way, if your third point is wrong, it doesn't necessarily mean that that is, if your third point does not fall on this line, it doesn't mean that your third point is incorrect. Maybe one of your 2 earlier points is incorrect. So I would check over the entire thing. Okay, now 2 points determine a straight line, and points that are very convenient to get when you're graphing a straight line are the intercepts. Okay, if you have a line, something like this, the line, okay, if the line is not a horizontal line or a vertical line, okay, it will cross both the x and the y axes. Okay, this is the point where it crosses the x-axis. This is the point where it crosses the y-axis. Now, when it crosses the x-axis, okay, it crosses at a point on the x-axis. Naturally, the y-coordinate would be 0. the x-coordinate of this point is the x-intercept. Okay, this is the x-intercept. Okay, when it crosses the x-axis, okay, it crosses at a point where y-coordinate is 0, the x-coordinate is the x-intercept. Similarly, when it crosses the y-axis, the x-coordinate must be 0, and the y-coordinate is the y-intercept. Now, if you're going to have only 2 points, okay, when you're going to, say, try to graph a line, these are very nice points to have because it tells you sort of, it helps you draw it a little more accurately. You want to have it cross the axes at the right spot. Now, how do we get these? Let's say we have an equation, something like (3x plus 4y equals 12). Okay, now we can pick any points we want. Any 2 points will determine the straight line. You can let x equal 1 and solve for y. You can let x equal 2 and solve for y. There are 2 points. Get a third one for a check, and you would have, plot those points, you'd have the graph of the line. Okay, but very easy points to get usually are the intercepts. Now, to get the x-intercept, find out where it crosses the x-axis, I set y equal to 0. Okay, I try to set y equal to 0 and solve for x. In other words, I'm looking for a point on the line that has y-coordinate 0. Okay, I want to force the issue here. I want to let y equal 0 and try to solve for x. If I can solve for x, that must be the x-coordinate that goes with y equals 0. And that would be the place where the line crosses the x-axis. So to find the x-intercept, we set y equal to 0. We get 3x plus 4 times 0 equals 12. 3x equals 12. X equals 4. This is the x-intercept. In other words, the line goes through the point 4, 0. To find the y-intercept, we similarly set x equal to 0. Okay, 3 times 0 plus 4y equals 12. 0 plus 4y equals 12. Y is equal to 3. We set x equal to 0. Find out that y equals 3. We get a point that has x equals 0. This is 3 is the y-intercept. So we have determined 2 points, okay, which are solutions to this, and they're very nice points to have because when we plot them, they're very easy to plot. We can get the picture of the line very simply. We have 4, 0, 1, 2, 3, 4, 0, and 0, 3. And there we have a picture of the line 3x plus 4y equals 12. Okay, if you want to check this, you can just arbitrarily pick a third point. Let's say x equals 1. If x equals 1, we get 3 times 1 plus 4y equals 12. 4y equals 9. Okay, 3 plus 4y equals 12. Subtracting 3 from both sides, 4y equals 9. Y equals 9 quarters. So the point 1 comma 9 quarters, or 1 comma 2 1/4, should also be on here. 1 over 2 1/4 would be right around here, and that is on the line. Okay, and this gives us a check that we have found the other 2 points correctly. Okay, now, before I finish this tape, I would like to spend a moment discussing the special cases. Remember I said ax plus by equals c, where not both a and b are equal to 0. This is a linear equation. Now, if b equals 0, you get an equation of the form x equals a constant. For example, something like x equals 3. On the other hand, if a were equal to 0, you'd get an equation of the form y equals some constant. For example, y equals minus 2. The graphs of these equations, okay? You see, if it had been, okay, we're trying to graph equations in two variables. We're thinking of, say, one of the a or the b being 0, but still we're trying to graph this in 2 dimensions. Okay, so unlike just the solution to a first-degree equation in one variable, here we're saying basically there are 2 variables. Okay, if x is equal to 3, okay, what I'm saying is that y could be anything. In other words, the graph of this, what are the solutions? The solutions are points of the form x equals 3, y can be anything at all. Now, where are these points located? Let's take a look. Okay, we want to graph in 2 dimensions. We want an x-coordinate and a y-coordinate. The x-coordinate should always be 3, but the y-coordinate is unspecified. So, for example, you could have the point 3, 0 as a possible solution, or the point 3, 1, or 3, minus 1, or 3, 2, or 3, 3, or 3, 4, or 3, minus 2, and so on. Where are all the points that have the property that their x-coordinate is 3? They happen to lie along a vertical line, 3 units to the right of the y-axis. X equals a constant will always be, okay, when you graph it, you will always get a vertical line, okay? Now, if the constant is positive, it'll be to the right of the y-axis, that number of units. If the constant is negative, the line will be located to the left of the y-axis, that number of units over. Okay, similarly, let's look at the line y equals minus 2. Here I'm saying that the y-coordinates of all solutions, of all points here, should be minus 2, but I don't care what the x-coordinates are. For example, you could have 0 minus 2. You could have 1 minus 2, 2 minus 2, minus 1 minus 2, minus 2 minus 2. These points all lie along a horizontal line, 2 units beneath the x-axis. Okay, that's where all the points whose y-coordinate is minus 2 can be found, on a horizontal line, 2 units under the x-axis. Okay, x equals a constant is always the equation of a vertical line. Y equals a constant is always the equation of a horizontal line. If a and b are not 0, you will get an oblique line, one that has both an x-intercept and a y-intercept. You'll notice that the vertical line has an x-intercept but no y-intercept, and the horizontal line has a y-intercept but no x-intercept. And this brings us to the end of this tape.